Now let's look at a wire itself and look at the electrons in the wire. Okay. Concept zero is that if we've got a charge, that's a current that's flowing this way, the nasty little secret is that, of course, the electrons are going the other way. Okay, we pretend like positive charge moves, but electrons actually go the other way, right? Notice that there's an electric field to the right, but the electrons being negatively charged experience a force that is to the left and drift to the left. Now, as you might imagine, right, a mole is a tremendously large number, and let's just imagine that every atom of this wire has maybe one electron or maybe two charge carriers that are free to move, right? You can imagine that there's just a bajillion of these things traveling along, whereas a coulomb is only, I think, say 10 to the 18th electrons, right? And so if you have a current flowing down this wire, the point is that these electrons move at an astonishingly slow velocity, okay, down the wire. But this electric field travels nearly the speed of light. So when you complete the circuit, this electric field appears, and then the electrons all begin to drift down the wire at some pretty low speed because there's a lot of them, right? In order for there to be say 1 coulomb per second, that's, just a fraction of a mole, right? So anyway, and then the other thing is that they don't just move in a perfectly straight line. They just kind of drift around, okay? They're free to move, and there's metals typically have these lots of unfilled orbitals, right, where they share electrons, right? These are metallic bonds, okay? This is our formula for current, and that V is the electron drift speed right there. This is the cross-sectional area of the wire in square meters, just like in resistivity. And then N is the conveniently calculated for us. Hopefully we won't have to calculate N, right? Because it'll have to do, N is some factor of the density, the number of electrons per atom, right? The density of it, which is kilograms, right, per cubic meter, must also have to do with the molar mass, right? Because we'd figure out how many moles, and also Avogadro's number. If we knew all those things, right, we could be clever and figure out the charge carriers per cubic meter, right? And then Q is the charge on one charge carrier, okay? They're allowing as to how perhaps we might have charge carriers that are not electrons. But, as far as I can tell, they're always electrons. So we're always going to use 1.602 times 10 to the minus 19th coulombs per electron, right? Okay. Now, if you look at the units that this thing has, we can figure that out, right? The units are coulombs per electron. Oops. Electrons per cubic meter. Right, that's what N is, right? It's electrons per cubic meter. Area is square meters, right? Velocity is meters per second. And then that Q is coulombs per electron, right? Okay, and then if we look at the units of this thing, right, this is N, those are the units of area, those are the units of velocity, and then the units of the charge, right? Notice that electrons goes away, meters cubed gets rid of meters cubed, and you end up with coulombs per second, which is equivalent to an ampere, right? So anyway, there we have it, right? That's the notion. That's the idea, the big idea here. Okay, so let's use this formula here, right? Okay, so let's see, a 2.4 millimeter diameter copper wire has a current of 5.8 amps flowing in it. What is the electron drift speed? So I is 5.8 amps. And then we are supposed to use 8.5 times 10 to the 28th electrons per cubic meter, right? That's at least a fairly large number, right? And then let's see, the diameter, we need to find the area, right? So the area is going to be pi times the radius squared. So I'm going to say that's 1.2 e minus 3, that's millimeters, right, squared. I think we're set to go, right? Let's just plug it in here. if I is equal to NA drift velocity times Q, right? Oh yeah, and then the Q we're going to use 1 electron charge. Okay, then the velocity, the electron velocity is I divided by N A Q. Right, so that's going to be 5.8 coulombs per second divided by 8.5 10 to the minus 28th electrons per cubic meter. The area is pi times 2.1, nope, 1.2 E minus 3 meters, and that's squared. Okay, let's see. And then Q is 1.602 E minus 19th, and that's coulombs per electron. All right, so let's see. Coulombs goes away. Meters squared gets rid of that, and then there's leaving 1 meter on the bottom of the bottom, so it's on the top, right? Electrons goes away, and you'll end up with meters per second. Okay, this is good. This is good stuff. Okay. 5.8 divided by parentheses 8.5 E28 times pi times 1.2 E minus 3 squared times 1.602 E minus 19, right parenthesis, which is the end of the denominator. And I'm getting 9.415 10 to the minus 5th meters per second, right? So 5.8 amps is at least, let's just say, a somewhat robust current, right? And so let's say you're doing this with the some wire in the laboratory, right? And the wire is 10 centimeters long. It would take, if it was 10 centimeters long, it would take 1,062 seconds, which is 17 minutes. It would take like 20 minutes for it to go 10 centimeters, right? So that's sort of an interesting thing, right? If it 10 centimeters, it takes 17.7 minutes. But understand that as soon as you throw the switch and the electrons start to move, they, at the speed of light, nearly all of them in the wire, right, almost simultaneously are moving at this, lickety-split, like little tortoises, right? The impulse, the actual electrical signal travels close to the speed of light. It's not the speed of light because it's a bit slower in wires. But anyway, there you go.